Hi, this is Mr. Green, and this is another in my geometry videos, and we're going to be looking at 3.7 and 8, I believe it is. It might be 8 and 9. Nope, I'm totally wrong here. Looking at my announcements, it's 8 and 9 that we're looking at. Okay? Parallel line properties 1 and 2. Well, didn't we talk about parallel lines last week, Mr. Green? Or last time, Mr. Green? Yep, we did talk about parallel lines. So we talked about the a couple of concepts about them. But what we're going to do this time is not just look at their angles and looking at testing conjectures about parallel and perpendicular lines. We're going to look at them from a slightly different perspective, okay? We're going to look at them from their converses. What? Converses? Oh my goodness, we're going back to lesson 2s again. Yep, we talked about corresponding angles last time. We said it was a postulate, and we said two lines are parallel, are intersected by a transversal, then the corresponding angles are congruent. But you notice it's an if statement and a then. So we can write the converse of it. We can take this and swap it for the other part, and what do we wind up with? The converse says if two lines are intersecting by a transversal and the corresponding angles are congruent, then the lines are parallel. How are we going to keep track of this? If the lines are parallel, you can prove angles are congruent. If the angles are congruent, you can prove the lines are parallel. So it depends upon what you're trying to prove. If you're trying to prove that the lines are parallel, you're looking for congruent angles. If you're trying to prove that the angles are congruent, then you have to say, I've got parallel lines. Okay? So that's what the converse of the corresponding angle theorem postulate is. What about these others, the alternate interior angles? You didn't see it down here, did you? It says the converse of the alternate interior angle theorem. That says that if alternate interior angles are congruent, then the lines are parallel. Same thing. I'm proving lines parallel. Why do I want lines to be parallel? Because if I can prove lines are parallel, then I know I've got a parallelogram. Oh, this is going to be easy because we're trying to get to the point that we know what things are. So if I can see lines that are where I've got alternate interior angles, alternate exterior angles, even same side interior angles in which the angles are supplementary, all we've got to do is say, using that theorem and the converse of it, we get parallel lines. That's what we're looking to do, is to wind up with parallel lines. For example, in this one right here, if we didn't know that these were the lines were parallel, if we knew that 7 was congruent to 3, those are alternate interior angles, and we could say the two lines going right to left would be parallel lines, this line here and this line here, by the converse of the alternate interior angle theorem. If we didn't know that angle 1 and angle 15 were, or if we didn't know the lines were parallel, but we knew that angle 1 and angle 15 were congruent to each other, we could say that these two lines were parallel based upon the alternate exterior angle theorem. That's what we're trying to get to, is that we can prove the lines are parallel, or that we can get to the point the lines are congruent, the angles are congruent. Here's an example. Here's a proof. It says, given that angles 1 is congruent to 3. Well, I always like to take my proofs and mark what I know. 1 is congruent to 3. That's those two right there. And angle 2 is congruent to 3. So those are congruent there. And they want me to prove, so they're wanting me to prove something. I'm going to put that in a different color so I know that when I get it, I'll have it done. They want me to prove that AD, that's this line segment there, is parallel to BC, that line segment there. They're wanting me to prove those two lines are parallel. Well, if those lines are parallel, you know what? One of the things I can see just by looking at it is that if 1 and 2 are equal, aren't 3 and 2 also equal? Congruent? Why would they be congruent? Symmetric property. Remember, if we've got 1 congruent to 3 and 2 congruent, they're congruent to the same things. So that would mean that 2 and let's see here, 1 and 3, 2 and 3, and then we're saying 2 and 3 are, that's the symmetric property of congruence. What are we doing? We just turned it around, didn't we? Symmetric property of congruence. We turned this one right here. We turned it around the other way. Kind of like the community property, but not quite. It just turns around. Okay? And then what they're saying is since the 3 is congruent in both of those two statements, I want you to notice 1 congruent to 3, 3 congruent to 2. Now that 3 can be eliminated and you can say that 1 is congruent to 2. 1 and 2 are congruent because of the transitive property of congruence. Can you see why in the last chapter I had you understand the symmetric property of congruence and the transitive property of congruence so that you would understand that those are the two properties we're using right here. And now that I've got that, I can say that AD is parallel to, AD is parallel to BC. Why in the world can I say that when I haven't talked about anything about up here? Well, I want you to notice 1 is here and 2 is here. Those are alternate interior angles to the lines AD and BC. Therefore, the converse of the alternate interior angle theorem says that these two lines are parallel. And that's all we're doing is using that converse theorem to prove those two lines are parallel to each other. So based upon what we've got here, did I get a parallelogram? Not quite. Okay? Why didn't we get a parallelogram? Well, we didn't get a parallelogram because we didn't prove that this line is parallel to this one. Could we? Well, I want you to notice 1 and 3 are congruent to each other. What kind of angles are those? Those are corresponding angles, right? Because I've got parallel lines right here and a transversal going this way. That means if these two are congruent to each other, that must mean that AB, is it A there? Yeah, AB is parallel to DC by the converse of the corresponding angle postulate. That means this quadrilateral in here, ABCD, must be a parallelogram. Ta-da, we got to a parallelogram. There's certain things we know about parallelograms then now, and we can use that information to go further in this proof and go further in what we're trying to use this for. Can you see how it all builds on each other and geometry kind of builds off of this information? Okay? Please, if you're sending me K-mails, I really do appreciate it when you're doing it, when you're telling me what your course and what section number you're in, because it really does help me find your records a whole lot faster and respond to whatever you're asking. I'll see you the next time I see you.